Hi guys, welcome once again to 100 Days Machine Learning Crash Course. Today we want to talk about different optimization methods for neural networks, which is really important when you want to train a neural network. Okay, so last session we talked about backpropagation algorithm to train the network. So now we have the idea of how the gradient descent methods work to train the network. Okay, so we want to learn some different variants of gradient descent algorithms to learn how to train the network. And in this session, actually, we don't talk about batch normalization. It is a regularization method, which we will talk about it in regularization session. So so we want to talk about different gradient descent variants for training the neural network. Okay, so for a linear neuron, if we use the squared error, we know that the squared error is something like this. So for a linear model, the error surface is something like quadratic bowl. In other words, if you plot the loss function, let's say this is loss, as parameter of W1 and W2, then you probably have something like this. And it is actually a 3D thing. And if you plot the contour for this graph, you have something like this quadratic bowl contours in here. Okay? But when you have a multi-layer network, you apply some non-linearities to these layers. So if you remember that we had something like these non-linearities to the inputs to get a multi-layer neural network. So in this case, the error surface is no longer a quadratic bowl, and it is a much more complicated shape. Maybe the contours are like this. Okay, but actually they are locally quadratic, because in fact we could write the Taylor expansion of them to approximate them with a second order Taylor very well. We will see that in the next slides. Okay, let's move on. So first we want to talk about mini batch gradient descent. So if you remember that in backpropagation we update the weights, or in general when we want to use the gradient descent algorithm, we use this formula to update the weight. Okay, but the problem is that for a very when we have lots of training data, then we know that the error is equal to sum over all of the training data of the loss function for each sample. Okay, and when you have lots of data, in order to just do one iteration and one update of W, you should calculate this term for all of the training data, which is really hard, because you should do the backpropagation algorithm to derive this term for each training data, and then it will take a lot of time to calculate this term for all of the training data, especially if your training data set is large. which is the case commonly in deep learning, because when you have, let's say we have 1 million images, then for each iteration you should calculate 1 million times backpropagation algorithm to calculate this term. So it is really expensive computationally. So instead of doing that, we could use mini batch gradient descent, which we talked about it. So in other words, instead of calculating the loss function over all of the training data, we just pick some random samples from the data set, or we call it a batch. So we extract a batch from the data set and then just run and calculate the backpropagation algorithm on the batch size data. Okay, so instead of having lots of computational costs in calculating the derivative, we just need to instead of, for example, 1 million times running the backpropagation algorithm, if we choose the batch size of 16, we just need to calculate 16 times backpropagation algorithm to derive this term. Okay, so this is a really good way to alleviate the problem of large data sets. So we just use smaller batches than the whole number of data to calculate the gradient on them and run the backpropagation. Okay, and we actually could do faster version of this and implement a faster version of this by vectorizing the calculation. So because we have, let's say we have 16 samples that we want to run the backpropagation algorithm for each of them, and we want to do the same thing for all of them. So we could somehow vectorize this operation with the GPU or with your graphic card to speed up the performance of the algorithm. Okay, so this is mini batch gradient descent. So probably your question is that what should be the batch size? If you have the batch size equal to 1, then probably your estimation from the gradient is not really good, or in other words, you have a high variance estimation for your gradient. So you have lots of jittering in decreasing the loss function, and also maybe it is not a very good choice performance wise, because you could not vectorize this in your GPU, because you just have a one sample. There are some common choices by the researchers and people that they use commonly in the especially image processing task. The batch sizes of 16, 32, 64, and 128 and 256 are commonly used batch sizes that people use to train the algorithm. Okay, so you could also try these batch sizes in your training network procedure. And if you note that all of them are power of 2, so 32 is 2 to to the power of 5, and so on. So this is because in GPU and in fact in your graphic card, lots of implementation of matrix multiplications and other stuff are very aligned with power of 2 things. So in other words, if you set the byte size as the power of 2, then you will have probably a faster performance for your training procedure. And also if you set the byte size equal to the number of your training data, it means that you are making the full batch training, and it is equal to the gradient descent algorithm. It is a plain gradient descent. Okay. So here we have a summary of what we said and what each of them has benefits and what are the characteristics of each of them. So in here, as you could see, for byte size equal to 1, we could not vectorize the calculation, so it is not really computationally efficient. For these byte sizes, or in the middle of byte size 1, or we call the stochastic gradient descent, and batch gradient descent when we have the byte size equal to n, between of them we have a good vectorization. We could vectorize the calculation, and we have fast learning with proper byte size. So you should try these byte sizes in your network probably. And if you set the byte size equal to number of training data, then you need lots of computational costs to just do one iteration, as we saw. Okay, so this is a nice representation for different batch sizes. So in full batch mode means that the batch size equal to number of training data. We have this line in here. So as you could see, these are the contours of the loss function. So because in the loss function we have all of the training data, then if you apply gradient descent with full batch on the on your loss function, then you probably will converge to a local minimum or to a global minimum if this is a quadratic bowl shape. You will converge to that without any these jittering ones. So the reason is that in this case we are minimizing, in fact we are estimating the gradient in each step with regarding to all of the training data. But if you use stochastic gradient descent, or with batch size equal to 1, the gradient, this mini batch gradient descent with batch size 1, it is, you have something like this, because in each iteration you just estimate the gradient with just one sample, so you don't have a very good estimate of gradients, so you could have something like this. But the good news is that we have some proof of convergence, that in this case we also have convergence for stochastic gradient descent, and between them, for example for 128 we have something between these two. As you could see in here, we have some jitterings, but we don't have the smooth version as smooth as this one. Okay, so for small training sets, when you have a small training data set, maybe less than 2000 or 3000, you could use full batch gradient descent. Depends on your machine that you do the training on that machine. So you could use different you could use the full batch gradient descent for small training sets, but for larger training data sets, you could use these common batch sizes to use the mini batch gradient descent. Okay. So if you plot the loss function based on versus the epochs, so it means that epoch means that let's say, so we know that the update rule is something like this, right? So the update rule, when we have the update rule with this formula, then after each step means that from t to t plus 1 we have one iteration. Okay, so if we do this for all of the training data, so let's say we have 1 million images, then let's say the batch size is 1. Then when we want to see all of the training examples, we need 1 million iterations in stochastic gradient descent, because the batch size is equal to 1. So every 1 million iterations is 1 epoch. Okay, so 1 epoch means that the number of iterations that you need to see all of the training examples. So in fact, if the batch size is, let's say it is batch size and the training data is n, then the number of iterations in each epoch is actually the number of your training data divided by the batch size. So it is 1 epoch. Okay, so in this case, when we have 20 epochs, if the batch size is 20 and the number of training data is 200, then it means that we have seen, or we have the number of iterations in each epoch is 200 by 20. It means that 10 iterations in each epoch, so we have 200 iterations when we have in this point, when we are in the point of 20 epochs. Okay, but the point of this plot is that when you use the mini batch gradient descent, you have something like this, or as you could see in here, you don't have a smooth thing, right? You have a trend in here to demonstrate to you that you are doing well for training your neural network in general, but for each batch you have lots of oscillation to update your network. The reason is that when you use the batch gradient descent or full number of training data, then the cost function that you are want to minimize is the cost function is actually the gradient that you are estimating is aligned with the cost function that you want to optimize. But when you use mini batch gradient descent, it means that you are estimating the gradient with limited number of training data, so your estimation is not accurate, so you have some jittering, or in other words, you are minimizing another loss function, which in fact is this loss function for just number of batch sizes in each iteration. So you have something like this for minimizing your network when you use mini batch gradient descent. Okay, so now we want to know what the problems with gradient descent that we have and how to solve some of them. We will talk about each of them in the next slide. So the first problem of gradient descent is poor conditioning problem, and the second problem is saddle points and local minima, and also the third problem is noisy gradients in stochastic gradient descent. When I say stochastic gradient descent, I don't mean necessarily batch size 1. I just want to note that instead of mini batch gradient descent, I say stochastic gradient descent. Okay. So what is poor conditioning? Let's say you have something like this. The contours of your loss functions are something like this. Okay. In other words, let's say you want to minimize. This is your cost function. So let's say it is x1 squared plus gamma x2 squared. Okay. If you use a large gamma, let's say 1000, then you have something like this. For gamma equal to 1, you have perfectly square, perfectly circular contours, right? So in this case, if you use gradient descent, then let's say we start from here, then if we move in the negative gradient, because the gradient is in this direction, so if we move in the negative direction of the gradient, we go to here, after here we will go there, and then to the minimum. So this is a really good case for gradient descent. But now we have something like this. What happens? So in here the gradient is, so hopefully you know that the gradient is perpendicular to the contours. So the gradient is in this direction. So now we want to move in the negative direction of the gradient. So based on the learning rate, we may go to here. After going to here, we should calculate the gradient in here. The gradient is in this direction, so we should move, let's say, in this direction with this step size. And you have something like this to reach the minimum, which is some kind of jittering, and it is not a very good way to reach to the minimum. Okay, so if you have a more elliptical contour, then you probably then the gradient descent takes a long time to reach the minimum. So we call this poor conditioning problem. Okay, so it means that your contours is not circular. It has a very good condition, but it is poor condition. Okay, as simple as that. So in here we could see that we have a jittering in this direction. So it is because the poor conditioning problem. Okay. So the question is there any way to train the neural network with this kind of loss function faster or more quickly? We will see that we could do some changes in the gradient descent algorithm to train the network more quickly. Okay, so this is the first problem of neural networks. The second problem is that the saddle points or local minima. So now we know that the loss function of neural network is highly nonlinear because we have lots of nonlinearity or activation functions in the loss function. So if we plot the loss function, we may have something like this. So if you use gradient descent, then if you start from here, then you probably get stuck in here, and you could not reach to here because in here, in this point, this derivative is 0 because you are in local minimum. So the w of t plus 1 is equal to w of t, so you're stuck in here. Okay, so this is one problem of gradient descent. The second problem is that many of times you have saddle points. So you don't have local minimum, but you have a 0 gradient in here. So again, you're stuck in here because of 0 derivative term in here. Okay. In fact, the saddle point is something like this. It means that in one direction you have a maximum, and in other direction you have minimum. So you have a saddle point in here. Okay, the gradient is 0, and the gradient descent algorithm gets us stuck in here and cannot move to this direction, which is the direction of the minimum. And this is also the visualization of local minimums, which gradient descent cannot perform as well on this kind of surfaces, and it cannot reach the global minimum. And in fact, the point is that for the neural networks, we have lots of saddle points. And let's see in here. So in fact, in neural networks, if we reach a local minimum, there are some papers that shows the local minimums in deep neural networks are not really bad one or bad local minimums. So, but the point is that the the bad thing is saddle points, and we have lots of saddle points in neural networks. Okay, and also the problem of plateaus, which is the regions near the saddle point. So near the saddle point we have something like this, and here's the gradient or the derivative is really low, or really small number. So if you calculate this number, because this is a really small number, then the W of t plus 1 is approximately equal to W of t, or in other words, you have very small steps in these plateaus, or you have a very slow progress, and this is another problem that we should solve. And also in stochastic gradient descent with batch size equal to 1, or small batch sizes like 16, the gradients are noisy. Why? Because when you have a large data set, then 16 samples from this 1 million data set to 1 million images to estimate the gradient could be really a noisy thing, and in other words, it has a high variance. So you probably have, as we saw, you have something like this to reach towards the minimum, and it takes a long time, and we should solve these problems. Okay, the first idea to solve this problem is the stochastic gradient descent plus momentum. So the idea of momentum is that we could assume that to mitigate the problem of noisy gradients, we perform some kind of exponential moving average from the previous gradients to consider them in the current step for updating the weights. So, or in other words, we want to physically, you could think of that as we have, so let's say we have a ball in here, and it comes to here. In here we have, let's say, the zero derivative, but because the velocity that it has in this point, so the velocity is in fact the result of the ball moving from here to here. So because of the history of this moving, we pass from this, in fact this is a saddle point. We pass from the saddle point, and so we could solve the problem of saddle point. So this is the idea of momentum. So we initialize the momentum with 0. Okay, so we could think of momentum as the velocity. So, and we actually show the change of W with dW. So first we initialize the V of 0, then in each iteration we calculate the gradient for the mini batch with backpropagation algorithm. Then we take some kind of moving average. We will see that why this is a moving average for your velocity. Then you update your weights with respect to this momentum. Okay, and typically the beta is 0.9 or 0.99. In fact, when you choose 0.9, it means that you are taking average from 10 last samples. When you have 0.99, it means that you are considering the gradients in the last 100 steps, and so on. So when you making the beta closer to 1, you are considering lots of other previous steps to calculate the gradients in the current step. Okay. Okay, now let's see how the problems now are changed. So now in local minima, we have zero gradient, but the velocity is not now zero, because in here we had some gradients. Now in here the v of w is not zero, so we could pass from this local minima. Okay, and it is also true for saddle points. In here we have some velocity and we could pass from here. And when we have the poor conditioning problem, then in here, let's say, because we are performing some kind of moving average from the gradients, then we could mitigate the poor conditioning. And as you could see here in the gradient descent with momentum, we have much more smooth path to the minimum. Okay, so we kind of solve the problems. To see how we are taking the average of previous gradients, let's say we plot some data. So the data is the temperature versus days. So we have some different days and we plot the temperature in these days. If we perform the v of dw is t minus 1 plus let's say this is t and this is t, then we could calculate, actually you could plug this v null into here to estimate v1 and plug that into the next step to the last step. If you calculate all of those, you could see that for different betas or for larger betas, you are taking more average from previous steps and you have more smooth approximation or more moving approximation from your last steps. And when you considering a smaller beta, then it means that your current steps is more important and you somehow ignoring really long previous steps. So maybe when you have 0.9, it means that you are looking at probably approximately 10 last steps to approximate your data. So as I mentioned, you could write the v of t, and so it is kind of exponential weighted average if you familiar with that. Okay, so in the first steps, we have a really small v of t, because we initialize v of t with 0, and in the first steps we have a small number of v of t. So to mitigate this problem, we perform bias correction. So we divided the v of t by a small number, so the result is a bigger number than v of t. So we call that bias correction. So if you note to that, you could see that it is equal to actually this factor in here. Okay. And when you have large t, so in the first step you have 1 minus beta, which was that factor that I mentioned. And when you have large t, in large t, because the beta is less than 1, then this term will approximately be 1, then you just have v of t. So in the next iterations, you probably could approximate this with just v of t, so it just affects the first iterations which we want to affect. But as mentioned in here, sometimes it is just not it is not implemented by the frameworks, and because it could just delay the training for some iterations, which could be negligible. Okay, so now we know the gradient descent with momentum. So we have two parameters in here. We have beta, which is typically 0.9, and we have alpha, which is the learning rate, right? So we have two hyperparameters for the gradient descent with momentum. Okay. And you could see the algorithm of the gradient descent with momentum in here. The next thing is Nesterov Momentum, which is actually a very similar thing to the momentum, but in the momentum, in the gradient descent with momentum, we calculated the gradient in the point of what we stand in the point in the time t, but in the Nesterov Momentum we calculate the gradient in the next step, in fact. So let's see from here. It is actually really more intuitive in here. So when we use the momentum, we use the gradient in the point of x of t, but when we use Nesterov Momentum, we use the gradient in x of t plus the rho vt, which is another point, or which is at some kind of next step. And the reason is that we had actually better convergence theorems for Nesterov Momentum, but they are not actually really practically different for us. Okay. So if you see, you could see in here the differences between the stochastic gradient descent with momentum, and the Nesterov momentum. So you could see that the Nesterov momentum has a better convergence in a comparison with SGD with momentum. So let's see, in here we have an interesting behavior. So because we have velocity in this direction, now although the minimum is here, but we have some kind of overshoot from the minimum because we have velocity in here, okay, and then turn back to the minimum. So you should note to this problem when you use momentum. Okay. Another method to do the optimization is RMS prop or root mean square. It is specifically designed to solve the poor conditioning problem. So let's see, in this case, what we want in fact to have bigger steps in this direction and small steps in this direction. In this case, we could have something like this. It is really desired for us. Okay, so we could somehow adjust the d of w to create these steps from these steps. Okay, so in RMS prop, we adjust the weights with the element-wise squared of the weights of the d of w. So we have the s of d of w, and we create a moving average of those s of dw's, which are kind of averaging over element-wise squared changes. Okay, so d of w is the change. So if we are in this step and we have two-dimensional thing, so in this case this is the dw1 and this is dw2. Okay, so we are doing the moving average for s of dw by getting the average, exponential average, and by considering the squared element-wise squared to the reason of getting a squared is that we don't want to negative and positive affect the scaling, because it is not actually important. So we have the squared in here, and when we want to change the weights, instead of just doing changing the weights with this d of w, we divided it or scale it by the squared by the root squared of s of dw. So in fact, now in this case, let me to oops. Okay. Yeah, that is good. Now let's say we are in here, and first s of dw is 0, so we calculate d of w1 and d of w2, which is this step, and we divided we calculate the s of dw because the d of d, let's say this is direction of W1 and this is the direction of W2, because in this direction we have a larger degree of dW, or dW2 is large, so dW2 squared is much larger than dW1 squared. So when we want to change the W in the direction 2, we have Wt minus dW over the squared of S of dW, which is larger for the direction 2. So in this case we probably have this step, and if we continue that, we have something like this, and this is what we desire. When we have large jittering in a direction, then the RMS prop scale it and dump it down, so the problem now could be solved. Okay. So in this case you could use also larger learning rate for the alpha, because it somehow to some degree it automatically adjusts the step size in different directions. Okay, so the algorithm for our RMS prop is relatively easy in here. This epsilon is for the stability of the algorithm. If we had S of dW equal to 0, then we had something to not have the crashing of the algorithm. And now we could have a comparison between stochastic gradient descent with momentum, and the RMS prop. So as you could see, the RMS prop is a really good way, and it is actually widely used in deep learning to optimize the networks. When we use Keras or TensorFlow, they have the RMS prop as the optimizer, and we could use them. Okay, so for the Adam, we are actually combining. So the Adam is the next optimizer, and it is in fact the abbreviation of adaptive moment estimation, and we are combining the RMS prop and momentum idea together. So it isn't a new thing actually. So we just need to calculate both of the momentum and the S of dW. Then we are adjusting the weight based on the momentums and scale them. Okay, and again, because of the problems of biases that we talked about we use a bias correction version of them. Okay, so this is the Adam, and most of the times Adam optimizer are really good in classification tasks and for CNN, and you could use it, but when you use RNN, we will see that later, RMS prop is a better choice. Probably we could not actually say it deterministically, but experimentally RMS prop is for RNNs is better and more stable than Adam. But for classification tasks and for CNNs, Adam is really good. So in here you could see the difference between the different optimizers. Okay, now I think that's it for optimization methods. Actually, we have some other methods to optimize the networks that but they are not commonly and widely used in deep learning maybe some second order methods to optimize the networks, but I think most of the times people use Adam, Armus prop, or gradient descent with momentum, and we will see that in Keras and TensorFlow how we could use them. Okay, I hope that you enjoyed from this session, and hope to see you in the next session. Bye.